What is up, amigos? Today we're talking about boundary layer momentum thickness. We're going through what it is and how to calculate it. And this ties into the last week's video, which you can find here, and boundary layers in general, which you can find here if you haven't seen them. So we're going through what it is and how to calculate them. First of all, what is the boundary layer momentum thickness? So let's say we have a regular pipe and we have one side here and the other side up here. So this is a surface and the flow is coming in here with a velocity u infinity. As it hits the wall, we know that a boundary layer will form and it will start to grow. And we have the other upper surface up here. So with the boundary layer momentum thickness, we want to figure out how much momentum is effectively caught up in this boundary layer and really how much of a deficit there is in the boundary layer of the free stream flow. So if we were to look at the velocity of this exact same boundary layer, at this point, let's say, we will see that the velocity profile might look like this. So this is in the x direction here, and this is in the y direction here. As you go up in the y, generally speaking, u will increase, so ux, y. So the boundary momentum thickness tells us if we have this boundary layer, which we see the velocity changes as we go away from the wall, we will have some momentum in this boundary layer, but there is obviously a deficit because there is this lower velocity than the free stream velocity and the velocity inside the pipe. So how much would we have to move the free stream flow away from the wall and to account for the lost momentum in this boundary layer? And as we go up, ideally we'll get to something called the velocity in the free stream, which is hopefully equal to the free stream velocity up here and hasn't changed. If it has changed, then we need to factor that in as uex, because as we go along in the x direction, the velocity here changes. So to calculate the momentum thickness of this boundary layer, we use delta 2 as opposed to delta 1, which was the displacement thickness from last week, and delta 99, which is the boundary layer thickness based on getting to the 99% velocity height, which is on the original boundary layer video we have from months ago. So delta 2 of x, so any point along in this x direction, equals the integral from 0 h on 2, and h is the distance from one surface to the other surface. So effectively half the distance between one surface and the other surface. So 0 to h on 2, the center line, of uxy. So if we're at this point x, then we integrate up in the y direction, divided by uex, which, as I mentioned, hopefully uex at any point is equal to u infinity. This doesn't change, hopefully, along the x direction in this center line. 1 minus uxy divided by uex dy. So we integrate in the y direction. And if we were to do this, we can find what the boundary layer momentum thickness is here. And this is just another way of characterizing what the boundary layer is, how thick it is effectively compared to the displacement thickness or based on the free stream flow. This is coming at it from a momentum point of view as to how much momentum we have kind of lost in terms of the boundary layer. So in terms of a laminar Blasius boundary layer, the momentum thickness, is equal to approximately 0.664 nu, the viscosity, x on u infinity and square rooted. And if we were to just take all the boundary layers in general and average them, generally speaking, delta 2 will equal about delta on x, where delta here is the velocity, boundary layer based on the 99% free stream velocity. So if that boundary layer is like, let's say 0.1 meters high, so 10 centimeters or 100 millimeters, then that's divided by 6, and that'll give you approximately delta on 2. Now this is based on, as I mentioned, a laminar boundary layer and a Blasius, not a laminar boundary layer. This is on an average boundary layer. This one is for the laminar Blasius. But this is just on average. But we know that from laminar boundary layers and turbulent boundary layers, this profile is different. And in next week's video, we'll be going through how to use these relationships to determine whether a boundary layer is laminar or turbulent. So that's the end of this video. Make sure to like if you liked it and click the subscribe button to see more. And I'll see you in the video. Peace, amigos.